Okay, guys. I wanted to start off by reminding you that your milestones were due on Friday. I'm not scaring you all to death now because they actually were due on Friday, which I got wrong last time. So the Chase told me that perhaps not everybody submitted their milestones to EasyChair. I think everybody remembered to email their milestones to their TA mentors, but I'm not sure that every group remembered to submit them to the EasyChair system. It's still open. If you haven't done that, do that right away, like now or right after class. The TAs are going to start assigning reviewers to milestones. So we need all the anonymous submissions up on EasyChair. And the instructions are down, they are down here. If you go to the project milestone 2, there's the submission and reviewing instructions. It has the instructions for submitting to EasyChair. Currently, the reviews, we have them being due November 23rd. That should not be a lot of work for you guys. I think probably something on the order of 2 or 3 is what we'll have you look at. And you're supposed to just follow these instructions down here, okay? So fairly cursory review, doesn't have to be super in-depth. Remember, these are intending to be helpful to your classmates, so try to make them so and try not to be critical. Okay, any questions about that? So last time we didn't quite finish all of coordinate descent. We left out some stuff on the graphical lasso in screening rules, and I did a poll on Piazza to see whether you guys wanted that. And the overwhelming majority vote was that you did want that, so this is a democracy. And could you guys see the poll results? I'm just kidding. Everybody wanted to skip it and to go on to dual method, so that's what we're due. So sorry, graphical lasso fans. The notes are there, but yeah, this is a democracy, and you guys did vote for skipping it. So we're going to go with dual methods. And this is, you could think of this as really maybe a 2-part lecture. The first, on this lecture, we're going to be talking about this phenomenon that happens in the dual called dual decomposition, which is a very useful thing practically to know about. And we're going to introduce ADMM, which is a method that's kind of born out of this, this dual decomposition observation. And then next time we're going to spend the entire lecture on ADMM. So today we'll just spend a bit of the N on it. So this is what we learned last time. We learned about coordinate descent, which applies to problems of this form. So f is g plus the sum of hi, where g is convex and differentiable, and each hi is convex. We call such a function h that decomposes like this into the sum of hi of xi a separable function. And these xi's, they could be individual coordinates. They could also be coordinate blocks. We're kind of leaving it ambiguous for now. These blocks don't have to even be of equal dimensions. So these could be just an arbitrary partition of the variable of the coordinates of x. And the method called coordinate descent, or we might call this block coordinate descent if these were actually of dimension bigger than 1, just repeatedly and cyclically updates each xi, fixing for the other, let's say, xj's, the most recent values. So let's suppose we fix some initial point x0, and then we optimize over x1, fixing x2 through xn. Once we solve for that x1, we move on to x2. We use the most recent value of x1, the one we just found. We optimize over x2, fixing x1 and x3 through n, etc. So this is sometimes called cyclic coordinate descent if we proceed through in this order 1, 2, 3, 4, etc. It's a very old idea, and it's hard to pin down somehow exactly when people started doing this in optimization. And I mentioned last time a bit of its history and how it's been underappreciated in optimization for a long time, but it's kind of there's kind of been a resurgence of interest recently because what people have found, particularly in problems that arise in machine learning and statistics, is that we often have a loss that's smooth and potentially complicated, but the regularizers we pick, at least in many cases, happen to be separable. And this method is very simple and easy to implement. It's a very portable, simple method. Careful implementations that use kind of a careful translation of the work at one coordinate update to the work at the next coordinate update they can achieve state-of-the-art. So we saw even in some simple examples like, for example, just even for solving a linear system, coordinate descent is competitive with conjugate gradient. And one cycle of coordinate descent has the same cost as one iteration of conjugate gradient. And for something like the lasso, one cycle of coordinate descent has the same cost as proximal gradient, but appears empirically to be converging faster, even versus, let's say, accelerated proximal gradient. Okay, and then there are many other implementation tricks we kind of mentioned last time, like active set optimization and this kind of stuff. And so with these together, they can achieve state-of-the-art for the problems that coordinate descent applies to. Doesn't apply to every problem, though. Okay, so that was just a recap of last time. So to talk about the dual decomposition, which is going to be the focus of today, we're going to have to recall some facts about conjugate functions. Okay, so I'm just going to remind you what a conjugate function is and then some of its basic properties. So remember that if you give me any function f, it doesn't have to be convex. It can be generic function. We can define something that we denote f star, and we call its conjugate. Sometimes it's called its convex conjugate, in fact, because this function is always convex regardless of what f was originally. Okay, and f star at y is defined as the maximum discrepancy we can make between y transpose x and f of x over all x. Okay. We saw that they arise frequently in dual programs. This is actually how we learned them, that there's a natural link between taking the Lagrangian of a problem and deriving the dual in conjugation, because we can just negate both sides of this and see this as negative f star of y is equal to the minimum over all x of f of x minus y transpose x. And this was a piece of our criterion, right? And this came from like an inequality or an equality constraint. This was the, let's suppose that we had a non-negativity constraint on x, so x bigger than or equal to 0, then this would be its associated dual variable for that constraint, and this would be a piece of the Lagrangian that we would be looking at. And taking a minimum over x would be an action that we do to get to the dual criterion. Right? So this is how they relate to duality, and this is why we can often express the dual very succinctly of various problems in terms of conjugates. It's because of this relationship. So we're going to utilize that today. And another property we're going to utilize today is this very important property that we just mentioned, I think, in the notes when we learned about conjugates, and that you're going to prove on the last homework. And the last homework kind of walks you through the steps to proving it. So there's a very interesting duality between functions, their conjugates, and subgradients, and it's stated as follows. If I have a function that's closed and convex, then, well, the first thing to remind you of is that if I take two conjugates, I get back the original function. Okay, so f star star is f. And furthermore, for a closed and convex function, x is a subgradient of the conjugate of f at y, if and only if y is a subgradient of f at x. Okay, so if we swap the roles of x and y, and we interchange f with f star, we can characterize conjugates, let's say, of f star in terms of subgradients of f star in terms of subgradients of f, and vice versa. This is what we learned last time, and what I said you're going to prove in the homework. There's a third equivalence, which comes out of the proof as well, of this equivalence, which is that equivalent to both of these statements is the following. X minimizes f of z minus y transpose z over all z. In other words, x achieves the min in this expression. So when you write down the expression for the conjugate of f star at y, x achieves the max. Or if I write down the expression for negative the conjugate of f at y, then x achieves the min. Okay, so these three statements are all equivalent. Okay, so I claim that at least one of these is actually fairly straightforward to see. So let's look at this problem, just give you a glimpse of why this might be. So let's look at this problem, minimum over all z of f of z minus y transpose z. So equivalence to having a minimum here is that I can take the subgradient of the criterion and set it equal to 0, right? That's just subgradient optimality. And if I have a minimum at x, then I have to take a subgradient, evaluate it at x, and that has to be equal to 0. So 0 has to be in the subgradient of this criterion at x, right? Which I can write as the subgradient of f at x minus, if I take the subgradient of this with respect to z and then plug in for x, well, the subgradient here is just y, right? Because it's just the gradient, and it's a constant, so it doesn't matter how I evaluate it. So that means that x being in the argument here is equivalent to subgradient optimality, which tells us that 0 has to be in the subdifferential of f of x minus y. Or in other words, just rearranging, y has to be in the subdifferential of f at x. Right? So that at least explains this equivalence, right? Okay, a very important special case of let's say this equivalence between subgradients of f star and subgradients of f is when f is strictly convex. Okay, when f is strictly convex, what do I know about this problem here, this minimization problem over z? What's the kind of the main thing we associate with strictly convex functions and minimizing them? It's unique, right? So I know that the minimizing value is unique, which means actually there is only one x which minimizes this, right? If f is strictly convex, so I can say x equals argument in that case, and that's equivalent to this statement. So there's only one x that's in the subdifferential of f star at y, right? What does that imply about f star? It implies that it's actually differentiable, right? For a let's say for a convex function, we know that the subdifferential is non-empty, and if it only has one element, then that is its gradient. Okay, so if f is strictly convex, then there's only, to repeat, this has a unique solution, which means that somehow there's a unique element of the subdifferential, which means that f star is differentiable. Okay, so we get this interesting implication that if f is strictly convex, then f star is differentiable, and in fact its gradient is equal to the argument, right? That's just calling its gradient x in this expression. So I can exactly characterize the gradient of f star at y by the following problem. I'm going to minimize over all z f of z minus y transpose z. Okay. Good. So here's an outline for what we'll do. We'll talk about dual ascent, dual gradient ascent. We'll talk about this idea of dual decomposition. Then I'll mention something called the method of multipliers, or the augmented Lagrangian. And then we'll introduce ADMM. We'll kind of state what it is and very basic properties about it. And next time we'll go into more details about it. Okay, so these equivalents here in this kind of special case, they actually tell us something very interesting about doing gradient ascent on the dual, which is that even if we can't derive the dual in closed form, we can still do gradient ascent. That is the idea behind, let's say, almost all of this lecture. So what I mean by that is, let's suppose that we have a problem that looks like this. I have some criterion f of x. I have some equality constraints ax equals b. It's a fairly simple looking problem. And let's suppose for now, and you'll see the motivation shortly when we talk about this decomposition phenomenon, let's suppose we wanted to actually, instead of doing something like projected gradient descent on the primal, we wanted to do gradient ascent on the dual. Okay, and the dual problem is exactly this. So I'll leave this as an exercise. This is just utilizing the definition of the conjugate. Form the Lagrangian, right? We get something like, let's say, f of x plus u transpose the quantity ax minus b, minimize out over x. Okay, the resulting thing is a function of u. You're going to maximize that function of u. That's the dual. And that function of u ends up being exactly this. Right? This first part comes from just the definition of negative the conjugate, and this minus b transpose u came from that. It was this left over. We had u transpose ax minus b added to the criterion for the Lagrangian, and then this just stuck around, minus b transpose u. Okay, so just check this if this link is unclear to you. This is its dual. And let's suppose we're in a situation where we don't know what the conjugate f star of f is in closed form. right? Or maybe we don't care to derive it because it's a complicated thing to try to look at. So I claim we can still do gradient ascent on this problem, or more generally, we can still run the subgradient method on this problem because of this relationship that we just learned. Okay? And what does this tell us? If we look at the criterion here, which I'm going to call G of U, that's the dual criterion. Okay, I can use just first of all simple subgradient calculus. This is really just the chain rule for the composition of a function with a linear function in terms of subgradients. To say that subgradients of G are A times subgradients of F star, evaluated at minus A transpose U, okay, minus B. Right, because I have two negatives here, and so I pull out a transpose of this operator, and the negatives cancel, and I just get A times the subdifferential of F star, evaluated at minus A transpose U minus B. Okay, so that calculation is hopefully straightforward. And now, what do we know about something like this? We know that, for example, X is in the, just from that equivalence we learned, it's in the subdifferential of F star evaluated at minus A transpose U, if and only if, okay, let's look back at this third statement here. X minimizes that function, right, minus, in this case, instead of y, we have u. Right? If and only if x is in the set of minimizers of this function f star, f of z, and I'm going to do minus z transpose minus A transpose U, right, which I can just write as the argmin over all z of f of z minus plus U transpose AZ. Okay, which means that to compute a subgradient of my criterion, right, let's suppose that I want to compute subgradients of my criterion G at a point U. Well, we already saw that was equal to this, right? And in order to compute an element of this subdifferential, I have to just solve the following minimization problem. So it's like an inner minimization I'm going to perform. I'm going to minimize out over all z, f of z plus U transpose AZ. I'm going to grab a minimizer. I'm going to plug in that minimizer here, call the minimizer x, and then I'm going to take as a subgradient of G ax minus b, just using that equivalence. All right, so just to summarize what we just said, that means that subgradients of G are ax minus b, where x is in the, x minimizes f of z plus U transpose AZ. That was just using the chain rule and that equivalence we stated that you'll prove in the homework. Okay, so what does the subgradient method then look like as an example on the dual, right? If we don't know f star, we can still do the subgradient method. We just do u equals u plus step size times a subgradient. So we're actually moving in the direction of the subgradient, not the negative subgradient, because the dual problem is in max, right? So instead of following the negative subgradient, we'll follow the subgradient itself. And how do we compute the subgradient? It's ax minus b. Well, we had to actually take x to be a minimizer of f of x plus U transpose ax. Right? So this is something we have to do to compute the subgradient. So once we have such a point xk, I'm calling it here, the subgradient of my criterion at the point uk minus 1 is just axk minus b. And I move in that direction. Okay, so these step sizes are chosen in the standard ways, right? I can choose them to be fixed if I'm willing to settle for something that's suboptimal in the limit, or I can choose them to be diminishing according to various rules if I want to actually converge to a solution to arbitrarily high accuracy. And really everything about this method is just, I mean, we know everything about this method just because we know about the subgradient method. And this is just a particular invocation of the subgradient method where we've computed subgradients via this relationship between f star and f. Okay, and again, to emphasize once more, there are no appearances of f star here. So this is a method we can deploy without knowing what f star is at all. If f is strictly convex, okay, then remember we know that that implies that its conjugate is differentiable. That came from what we said a few minutes ago. And so there's actually a unique minimizer here. So every time I look to minimize f of x plus u transpose ax, there's only one minimizer, right, because f is strictly convex. And that notation doesn't make much of a difference. I can just set x equal to the argument rather than saying I'll take one of the minimizers. But that makes this dual gradient ascent. Right? Now we're actually computing gradients. And it means that we can do things like backtracking, as an example, to compute the step sizes here. Okay, so, or we can take the step sizes to be large and fixed, 1 over less than or equal to 1 over the Lipschitz constant of our criterion, and we can still get away with converging to an optimal solution. All right, so that's dual subgradient method. This is dual gradient ascent. And there's no appearances of f star whatsoever. Okay, and the last comment is that you can apply acceleration, you can apply proximal operators, all in the same way as you would in the primal. This is just, the standard methods that apply to the dual. The only catch is that we are computing gradients or subgradients in a clever way, right, that don't require us to know f star. Let me pause for questions before we move on. Okay. So there's an interesting link between smoothness of f and f star, and we're going to use this to motivate statements about how fast we converge, for example, in terms of dual gradient ascent for this problem. Right? And here is I think, a very useful equivalence. It gives us even more information somehow than that equivalence we had between subgradients of f star and subgradients of f, and that is the following. Suppose f is closed and convex, okay? Then the following two statements are equivalent. F is strongly convex with parameter m, okay? Or f star is differentiable, and its gradient is Lipschitz with parameter 1 over m. Okay, so there's a very nice duality between strong convexity and Lipschitz and the gradient being Lipschitz as a move between f and f star. Okay, we already kind of saw a bit of this direction, right? Because we said that if f was strictly convex, then that implies that the gradient is Lipschitz. We already saw it came directly from the previous equivalences we saw, but this is a much stronger statement. We actually can characterize, let's say, the curvature of f and its conjugate in terms of the other's curvature, right? This is saying something like if f is sufficiently curved from below, then the gradient of f is sufficiently curved, of f star is sufficiently curved from above, and vice versa. I guess let's go through the proof of one direction. The proof of the other direction is a little bit more difficult. So I have the proof in the slides for both directions. Let's go through maybe just the first direction for the sake of time. And you can take a look at the reverse direction if you're curious. Okay, so remember that we have this basic fact about strongly convex functions, which is that if this is the basic fact, okay? If I have a strongly convex function, then I can lower bound my function. Suppose g is strongly convex with the parameter m. I can lower bound my function by a quadratic around any point x, and it's in fact just exactly this quadratic. Right? This is true for any x and y. For a strongly convex function g with strong convexity parameter m. And in the case when this is 0, right? For example, if x minimized this function, then the gradient would be 0. We're looking at now a convex differentiable function. And this becomes just g of y plus m over 2, the norm of y minus x squared. Okay, so just to paraphrase, if I have a strongly convex function that's minimized at a point x, this should say g of x. I'm not sure why I wrote g of y there. then I can always write for any y, g of y is bigger than or equal to g of x plus m over 2, the norm of y minus x squared. And now we're going to apply this, okay, to in fact this exact inequality here to in fact two different functions. The first function we're going to look at is it's just this one, g of x. Let's call this maybe gu of x equals f of x minus u transpose x. Okay, what is the minimizer of this function? I claim we actually know it exactly. What is the minimizer of this function? Comes from this equivalence. Look at the bottom one. The minimizer is in fact, because f is strictly convex, right? The minimizer is just in fact, let's call it x sub u. It's just the gradient of f star at u. Right? That's just exactly the third equivalence here. Okay, so what that tells us is that for any y, right, we're going to get g of y being bigger than or equal to, let's write it like this actually, let's just write it out. We're going to get f of y minus u transpose y is bigger than or equal to f of xu minus u transpose xu plus m over 2 y minus x squared. Okay, that's one thing that we can conclude. Let's look at a different function now, and we're going to derive two inequalities of this form, and we're actually going to add them together. Let's look at, for another fixed point at the moment, v, the function defined by f of x minus v transpose x. Well, it's the same story. The minimizer is just xv, which is the gradient of f star at v. Right? And we also know that for any y, the following is true. Okay, so we have for fixed points u and v, we have the following inequalities. And this came from strong convexity. And now I'm going to, in this one, I'm going to try y equals xv. And this one, I'm going to try y equals xu. So I'm going to plug in, for example, for y here xv. And here I'm going to plug in for y xu. And I'm going to add those two together. Okay. Right. Okay, so in doing so, I'm going to get f of xv minus u transpose xv plus f of xu minus v transpose xu is bigger or equal to f of xu minus u transpose xu plus f of xv minus v transpose xv plus, now it's just m, because I have two copies of the, this should have said xu, that should have said xv. I have two copies of the same thing, it's just the difference between xu minus xv norm squared. Okay, that just came from plugging in for different values of y in these two and adding them together. And I'm going to cancel now common terms of f on both sides. Okay, and so what I should get now, assuming I haven't made any arithmetic errors, is I should get the following. I should get u minus V transpose XU minus XV is bigger or equal to M times XU minus XV squared, right? So I'm just moving U transpose XU to the other side, and I have U transpose XU minus U transpose XV. That's just exactly this first bit. And I'm moving V transpose XV to the other side, and it's the same story. Okay, I just collected the terms involving V, and it's here. So that's the implication of the last statement here. And now for the final step, I just use Cauchy-Schwarz. So I just use Cauchy-Schwarz on the left-hand side. I'm going to upper bound this by the product of their L2 norms, and I get, and I'm going to divide by the common appearance of the L2 norm of XU minus XV on both sides, and I get XU minus XV is less than or equal to 1 over M. I just divide both sides by M, the norm of U minus V. And remember, this thing is exactly equal to, what are the minimizers? I just used this notation for convenience the whole time, but the minimizers are exactly this, are exactly the gradients. So this is a statement of Lipschitzness of the gradients. Okay, and the Lipschitz constant is just 1 over M. Okay, so that was a proof of the one direction. Right, we just proved that if F was strongly convex with parameter M, that implies that the gradient is Lipschitz with parameter 1 over M. And the reverse direction is slightly more involved, but I think it's fairly similar in spirit at least. Okay, and that's down the next slide. So why do we go through this trouble? We went through this trouble because I wanted to portray to you that somehow what we know about this method, dual gradient ascent, is very analogous to what we know about gradient descent on the primal. So let's look at the implications of this. Remember, we wanted to minimize F subject to AX equals B. That was our original problem. Okay? And that's this problem right here. And we have this method for doing so. Okay, yeah. Is there a question somewhere?
Yes. Is it possible to explain more general in not the pure convex case, but something about like the eigendirections that Hessian lying up between F and contradict?
Good question. I might push like a detailed discussion of that till maybe after class, but maybe let's say in simple cases they are the same directions. So like the simplest case you can maybe believe is when F is quadratic. So if F is quadratic, then like if F is this function, okay, then F star is this function. So they have the same spectrum and the same eigenvectors. So beyond that, you're asking if I can kind of learn details of curvature from using one to the other. I would guess the answer is yes, but I think somehow we'd have to be looking at things that are kind of close to quadratic to begin with. But it's a good question. This is just a statement, of course, about the smallest and largest eigenvalues. Okay, so let me motivate why we went through this trouble really quick, and then I'll tell you the implications for convergence. We're minimizing this function subject to AX equals B, and we have this algorithm. Okay, and now it's natural to ask how fast is this algorithm going to converge? And well, what we know about gradient, let's say descent or gradient ascent analogously, is that it converges at a certain rate when we have that the criterion has a Lipschitz gradient with a certain Lipschitz parameter. Okay, so we're going to try to ask when is this thing have a Lipschitz gradient? Well, we know when it has a Lipschitz gradient. It has a Lipschitz gradient when, by this equivalence I just told you, when this thing is strongly convex. Okay, so what we see is that if F is strongly convex with parameter M, then the dual criterion is going to be has a Lipschitz gradient with parameter 1 over M. Okay, from what we just learned right here. from this equivalence right here. And that means I can take step size as 1 over the Lipschitz constant, which is 1 over m, which is m. And I can expect gradient ascent to converge at the standard rate for that case, which is 1 over epsilon. Okay? So now you're looking at this and you're thinking, well, this seems really bad because I'm in a case where I have strong convexity and I'm getting a sublinear rate for minimizing my function. All right, I have strong convexity of f, I have an equality constraint, I'm running dual gradient ascent, and I actually only am getting a sublinear rate, 1 over epsilon. I'm not getting something like log of 1 over epsilon, which that's what we would expect somehow in this case. But there's a subtlety here, and everything is fine. The world is just. It's just that when we analyzed convergence for strongly convex functions, we always assumed that in addition to strong convexity, we had the function being smooth and having a Lipschitz gradient. It wasn't just strong convexity analysis. We actually used both. We had to sandwich our function by a quadratic in order to get that linear rate. So we had to assume that the function was strongly convex and it had a Lipschitz gradient. Okay? It turns out that for just strongly convex functions, strongly convex alone does not give you a linear rate. You need kind of both sets of assumptions, as I just said. So in that case, if we assume that f is strongly convex with parameter m and it has a Lipschitz gradient with parameter L, then we should expect a linear rate in this case, because that's what we would get from our first order methods theory. And what this last equivalence tells us is that actually being strongly convex and having a Lipschitz gradient on f, that is equivalent to the same thing happening on f star. Right? It's just using this implication for each of those conditions. So if f is strongly convex with parameter m, grad f is Lipschitz with parameter L, then f star is strongly convex with parameter 1 over L, and grad f star is Lipschitz with parameter 1 over m. Okay, from that equivalence. And in that case, we know that we can apply dual gradient ascent with particular step sizes. They're just 2 over strong convexity constant plus Lipschitz constant, and we get the linear rate we expect. Okay, so in other words, nothing is lost moving to the dual. The convergence is exactly the same. We have to just be clear about what we're assuming. All right, any questions about that? So here's the reason why we went to all this trouble. You might wonder why we go to all this trouble. It's for this reason specifically. It's that if we have a problem that partitions nicely into blocks of variables, so f is separable, okay, but we have an equality constraint, then it's not obvious what to do in the primal. Okay, if we didn't have this equality constraint, if I told you to minimize a function that was the sum of fi of xi, then you would use the fact that it was separable and you would actually solve for each xi individually. Right? It would be immediately decomposable. If you had B parallel processors, capital B parallel processors, you just would solve all these problems in parallel. Right? And then you'd collect the answers for each block. With this equality constraint, that strategy at first pass is ruined. Right? This is tying all of the variables together, so you can't really do that. The beauty of what we just learned is that the dual decomposes. Okay, the dual actually decomposes, and we can even solve for the gradients in dual gradient ascent in a decomposable fashion. So if we go to the dual, we apply that method we just learned, we can actually take advantage of the fact that this is separable. So to see that, we're going to partition the columns of A accordingly. Right? So we have some partitioning of X. We're going to partition the columns of A in the same way. We're going to call that A1 through AB. And it's a very simple, but it's a powerful observation and calculation of the gradient in the dual, or subgradient in the case that f is not strictly convex. And it's that this minimization here, okay, which we typically have to perform in order to get a subgradient or gradient, it decomposes into separable problems, right? Because I have to take, according to our last rule, just I have to minimize f of x plus u transpose ax. Well, f of x is the sum of fi xi, and I can write this thing, right, as just u transpose times the sum of ai xi. Okay, and I can just bring them into the same sum. So in case that one last step wasn't clear to you, if I minimize the sum of fi of xi plus u transpose ax, that's equivalent to minimizing the sum of fi of xi plus the sum of U transpose AI xi. I'm just writing a block decomposition, taking advantage of my block decomposition for A now, right? Which is equivalent to minimizing, right, just Fi of xi plus U transpose AI of xi. And now I have, let's say, B separate minimization problems, and I can solve each of these individually, right? The dependence on xi is limited to the ith term in this sum. So it's a super simple observation, but it's a very powerful one in practice because I can perform gradient ascent now, and I can actually calculate things in parallel. Right? So what I do is I actually just calculate for each block. I solve a smaller problem, which is minimize over all xi, Fi of xi plus U transpose AI xi. I collect all of those, and at the end I multiply that x by A. I do Ax minus B, and that's my gradient in the dual. Okay, so dual decomposition is just application of dual gradient descent to this problem. It looks like this. Solve for all these components that are going to make up the gradient. Then I form the gradient, which is just Ax minus B, or in this way I'm keeping the block decomposition of A transparent. And that's my gradient. I just perform a gradient step now in the dual. And sometimes people call these the broadcast and gather steps. So if you think about maybe an infrastructure for implementing this, I have a central node. Okay, and that central node, let's say, keeps a copy of the dual variable that I'm currently working with U. And the first step is to broadcast U to each of these individual units. So I have B units. Let's say I have B processors. Each processor gets a copy of the most recent U, and each unit solves a single one of those problems. Minimize Fi of xi plus U transpose AI xi with that most recent U, and it sends back the x that it found. Okay, and so they all get sent back to the central node, and the central node aggregates them and forms this gradient Ax minus B, and it makes a gradient step, gets a new U, and then broadcasts them back, gathers, etc. Okay. Okay, let me tell you about what happens with inequality constraints rather than equality constraints. And then I think probably we can take a break after that. So with inequality constraints, let's suppose now instead of having Ax equals B, I have Ax less than or equal to B. Okay, the dual problem you can check is exactly this one. We wrote down here. With an additional restriction on U, the only difference is that I'm constraining U to be non-negative. That's the new dual problem. So U has to be bigger than or equal to 0 in every component. So what would we do now? We would do projected gradient ascent in the dual, right? We take a gradient step, and then we'd project onto the positive orthant in the dual, so the set of all U's for which U is bigger than or equal to 0 in every component. And what's the projection onto the positive orthant? It's super simple. It's just the positive part operator, right? If I have anything that's negative in any component, I set it equal to 0. So that's projection onto the positive or non-negative orthant. So the only difference in the algorithm now is, okay, again, I compute the gradient or the subgradient if this is not unique. I take them all together. I perform let's say in the case that it's unique, I perform a gradient ascent update. And then I project that onto the non-negative orthant, which means that I just take the positive part of every component. Okay, I throw out the negatives. I set the negatives equal to 0. That's all I do. And this is exactly projected gradient ascent on the dual. Okay, so nicely, we've just maybe vastly generalized this problem from looking at affine spaces as our constraint set to arbitrary polyhedra. And the algorithm didn't get much more complicated. It still is completely decomposable. We can still solve this in parallel. It's just that the aggregation is like slightly modified. So economists like this method, and economists write a lot about dual decomposition because it has a natural interpretation. Specifically, this problem with the inequality constraints has a natural interpretation. Okay, and I took this actually from Lieven Vandenberg's, from his notes. So here's the interpretation. Let's suppose that I have B units in a system, okay, and each unit gets its own decision variable. xi, which tells us how to allocate certain goods. Okay, I have a bunch of units, decision variable xi for each unit I. And these constraints, okay, these ones here, they're limits on shared resources. So every row of A corresponds to a resource, and I can't use up too much of that resource, so that's what that inequality constraint is telling me. What I can think about the dual variable then, every component of the dual variable, okay, I can think about each component. So I have one component of the dual variable per row of A, right, because I have one dual variable per constraint, and I have an inequality constraint per row of A. I can think about the dual variable as the price of resource j. I can interpret it as being the price of resource j. And I can't make prices in this case negative, right? So that's why I'm having this non-negativity constraint on u. What is the dual update? Let's just look at the dual update in a more compact form. For every resource j, I take uj to be the old value of uj minus t times sj, and then I take the positive part. So if this was negative, I set it equal to 0. If it's positive, I keep it as is. Where sj, okay, is, or rather s, the vector s, is b minus a times x. It's the slacks. It's the amount left over from each of those resource constraints. So it's the amount you have not used up so far. So let's look at this in two cases. Okay, in the case that resource j is overutilized, I'm trying to use too much of it. Okay, this s is going to be negative, right? 'Cause I'm going to have something negative left over after I try to take this, this step. And I'm actually going to be increasing uj then, because I'm going to be subtracting off t times sj, and sj is negative, which means that I'm going to increase the price of uj. So if the resource is overutilized, I'm going to jack up the price to make sure people pay more attention to it. If the resource is underutilized, so if this is actually positive, then I'm going to be subtracting that from uj. So I'm going to be making uj smaller and decreasing the price. And this positive part is just saying never let the prices get negative. Okay, so I think it's a very natural interpretation for this dual decomposition algorithm. All right, let's take a break, and when we get back, we'll talk about how to improve convergence for this method. Okay, guys, we're going to continue on. So, I didn't really, I guess I did not give more details than this, but there's one disadvantage of dual gradient ascent. This is a major disadvantage, in fact, which is that we require strong conditions to get convergence. Now, that seems a bit contradictory to this slide, in which I told you it was the same conditions as what we would need in the primal. Right? The point of this slide and the point of the equivalence before was that somehow I was trying to convince you that we get the same convergence rates in the dual as in the primal. However, there's actually one important caveat, which was down here, which I didn't say out loud, which is kind of obvious in hindsight, is that all of these results here describe the convergence of the dual objective to its optimal value, and the dual iterates, in the case of strong convexity and Lipschitz gradient, to the dual optimal point. They don't describe what happens in the primal, right? Because we're just applying our theory for gradient descent or ascent on the dual. Okay, so these conclusions are about the dual objective. Ultimately, we don't care about the dual objective, right? We care about the primal objective. We care about convergence in the case of, let's say, strong convexity plus Lipschitz gradient, convergence of the primal iterates to the primal solution. And what we've done is we've talked about how fast we converge in this space. So it's not actually trivial to push that to something in the primal problem. And in fact, even under the conditions I listed, the iterates you get from dual decomposition, they can be infeasible for the primal in the limit. Okay, so just ensuring that somehow we get something that actually meets ax equals b requires more conditions. So the disadvantage of dual decomposition methods is that if we really cared about the primal, they actually don't have great convergence guarantees on the primal problem, right? Translating these iterates to what happens to x here, right? We're talking about what happens to u. That's the standard results for gradient ascent. Now, if we care about the primal, we're asking about x itself. So that's the major disadvantage, and there's some literature which places kind of more conditions on the problem in order to try to guarantee primal convergence. And that's one route you could go down. Another route you could go down is to actually transform the primal problem so that your problem is smoother and is more favorable in some sense. And that's sometimes called the method of multipliers, but it's better known as the augmented Lagrangian method. Okay, and I think it's a very clever thing to do in one way. It's a very clever thing to do in one sense. So what we do is we just add to the primal a quadratic term, okay, that looks like the norm of ax minus b squared, and this is called the augmented Lagrangian parameter. So rho is, now it's arbitrary. Okay, in doing so, notice that we haven't changed the problem at all because the feasible set is ax equals b, so if x is feasible, that contributes nothing to the criterion at all. Right? It's just adding 0 to the criterion. But if we went through and we actually looked at the calculation for the gradients in the dual, we'd see that actually we've changed things in a non-trivial way. Even though this is equivalent to our original problem, it leads to a different algorithm in the dual. And that's because where we had f before, now we have f plus a quadratic, and that gets propagated into this minimization. So where we look for gradients, we actually minimize now f of x plus u transpose ax plus this other piece of the criterion, rho over to ax, the norm of ax minus b squared. Okay, so this will give us a genuinely different value of x when we go to compute this at every iteration, which is going to actually alter our gradient for our gradient ascent update. Okay, and the augmented Lagrangian comes from the fact that this would have been the Lagrangian, right, without this, and now this is something that we're adding to Lagrangian, so it's augmented. So that's actually, in some sense, a good thing because it makes the problem smoother, and hence it actually aids convergence. And what some of the literature, old classic literature, shows is that this method converges in the primal, so we get a convergence of x here under weaker conditions than what we required for dual decomposition, where this rho is 0. But it's also hurt us in one way. What's the way in which this has hurt us? It's not decomposable, right? If f was a separable function, then we've ruined that. So look, if f is separable, then somehow this term still groups all of the x's together, and we're in trouble because we can't solve for the gradient in parallel. Okay, so in one way it's helped, another way, in a major way, it's actually hurt. We've ruined decomposability. So before we talk about where to go next, which you can tell is ADMM, based on the kind of the outline, I want to motivate why we use rho here. Okay, because we're going to do the same thing in ADMM. Usually this is a step size t, or tk. I would usually try to, let's say use backtracking if this was unique to find a step size. But I've actually fixed it at rho here, and that rho was what appeared here. So there's a specific reason for that, and let me motivate why that is why we make that choice. Well, if I look at essentially the stationarity condition for this problem, for this subproblem, or the subgradient optimality for this problem, right? It is this: 0 as a subgradient of f of x plus A transpose u plus rho A transpose AX minus B. Right? That's just taking a subgradient here. These things are all differentiable. I'm just taking their gradients with respect to x. So that is what subgradient optimality tells me about xk. xk has to satisfy this. Okay, and then look, if I were to take a gradient ascent update with step size rho, then this term right here, this would all this be uk. This would be my next u. Right? So I can just call this A transpose uk under that definition for the step size, setting tk equal to rho. So I see that 0 is in the subgradient of f of xk plus A transpose uk. What does that look like now? That is actually, if I look back on my original problem, without this at all, that is the stationarity condition for my original problem unperturbed. Right? That would be taking the Lagrangian, minimizing it over x, setting it equal to 0. It would be exactly this condition. So we can see that somehow this choice of step size plus the fact that we had a quadratic we added to our criterion, it's made it so that if I look at any primal dual pair in any one iteration, they're satisfying they're satisfying stationarity for the original primal problem, the stationarity condition. Okay, so as long as I can satisfy feasibility, then the limit, I know I'm going to converge to primal and dual solutions jointly together from the KKT conditions. So that's a kind of a hint as to why this converges better, and also why we choose the step size here to be rho. Okay, and the convergence analysis you'll find is all about showing that somehow we get ax equals b in the limit. So we actually get the KKT conditions, and we converge to a primal dual pair. So the advantage is much better convergence properties, as alluded to kind of by this. The disadvantage, as pointed out, is that we lose decomposability. So the separability has been ruined by adding this term to the criterion when we search for the gradient in the dual. So in comes ADMM, okay, which is called the alternating direction method of multipliers. So we can think about augmented Lagrangian as the method of multipliers. This is a modification of that. And alternating direction kind of tells the story, or ADMM for short. It's trying for the best of both worlds. So it's trying to retain the convergence of the method of multipliers, but also retain the decomposability of dual decomposition. And just like coordinate descent, this is actually an old method. People, at least in the 70s, were looking at ADMM. But just like coordinate descent, this didn't become popular until recently, even more recently than coordinate descent effect. I'd say in the last, like 10 years. Okay, so ADMM applies to problems of this form, okay, where we have a criterion that splits up into two pieces, f of x plus g of z, and we have equality constraints of this form, ax plus bz equals c. So if we don't have this form, then as we're going to see in ADMM, which is often the case we saw in deriving duals, we can manipulate our problem to make it fit this form. So even if our criterion doesn't obviously have this form, then we can often introduce auxiliary variables to make it fit this form. So just as before, we're going to augment the objective. So now think about maybe xz as one variable. Okay? And what I would do according to the method of multipliers is I would augment the objective. I would just add rho over 2 times the residual from this equality constraint squared. And I would define an augmented Lagrangian. Okay, everything so far is the same as method of multipliers. There's just one key difference coming up. Okay, but the only reason this looks slightly more complicated is that we actually have now we've decomposed our primal variable into x and z, but it's the same story otherwise. Okay, so the augmented Lagrangian is f of x plus g of z plus u transpose the residual from the constraint plus this piece, the augmented part, rho over 2, the norm of ax plus bz minus c squared. So what would the method of multipliers do, or the augmented Lagrangian method do? It would look for the minimizer of this augmented Lagrangian over the primal variable, which is xz jointly. Okay, so it would jointly minimize this over x and z for a given u, and then it would do a dual gradient ascent step with that updated variable xz. What ADMM does is it actually splits up that minimization into 2. That's the only difference. And hence the name alternating direction method of multipliers, because we first look at the x direction, then the z direction. So we first minimize the Lagrangian over x with z and u fixed. Then we plug in for the most recent value of x, just like we would in coordinate descent. Minimize out over z with x and u fixed. Then we take a dual gradient ascent step. Okay, so just stare at this for a second. The only difference here between ADMM and method of multipliers is that we split up over x and z. We've actually forced ourselves to minimize this separately over x and z. Okay, so I'm going to tell you about the convergence guarantees. And I'm going to tell you, I'm going to give you a very easy application of ADMM. And then if we finish early, I might actually start the ADMM lecture because it seems very natural, and there's quite a lot I want to say in that lecture. So you're not going to tell just from this lecture about somehow how applicable ADMM is. It still might seem like it's a rather restricted form. That's actually not true. It's very widely applicable. We have to just kind of massage problems to make it fit ADMM form. So what do we know about ADMM first? I'll tell you what the kind of generic convergence guarantees are. So under modest assumptions on f and g, so closed and convex is good enough. Do you have a question?
Yes. Step back for a second. said this is a widely applicable method. Can you talk a little bit about how it fits into the previous methods we've seen and when we care about using these class of methods?
I can. Let me maybe push that. This seems like I could do that at the end of the lecture as well. So let me kind of get through what we know about 8mm, and then I'll tell you a bit about where it lies in the scope of things. So under these kind of modest conditions on F and G, so for example, closedness and convexity is enough, which is kind of a standard thing we assumed all along. And we don't even need A and B to be full rank, so these can be rank-deficient matrices. We have the following about 8mm. So we get that the iterates produced are primal feasible in the limit. So we're going to actually get X and Z that meet the equality conditions in the equality constraints in the primal. We have that the primal iterates converge in terms of their objective value to the optimal objective value. And we get dual convergence. We get that actually the dual variables converge to dual solutions. So this one, the fact that we get the strongest conclusion in the dual kind of should make sense too, because after all, we're doing gradient ascent in the dual, kind of. So we should be seeing kind of a very strong statement about the dual. These are nice kind of artifacts of the fact that we've augmented the Lagrangian. We actually get primal guarantees as well. Okay, so the proof is not very difficult. I think it kind of uses standard techniques you've seen already. This monograph by Stephen Boyd and a lot of his students is one of the reasons why 8mm has become so popular recently. It kind of really put it in the mainstream. But like I said, it's been around since the 70s. In terms of convergence rates, like coordinate descent, this is actually still an active topic of research. So it's not something that's like a standard result, just like we saw for other methods. This is still being worked out now. Roughly speaking, this behaves like a first-order method. So you should think about these as being on par with first-order methods. But it's much more flexible. And as we'll motivate in the next lecture, it allows you to kind of decompose problems and solve things in parallel when that's not obviously, let's say, the structure in the problem to begin with. So there's a lot of theory still being developed for how fast it converges, and I gave some references here, but I think it's still somewhat of an open topic. So let me tell you about scaled form, and then I will tell you about an application of 8mm, and if there's time, I'll either move on to the next lecture or I'll talk about kind of the scope of where things fit in. So we typically don't use 8mm in this form. Okay, there's a more convenient form to write things in, and that's scaled form. The only difference is that we actually are going to define a modified dual variable, a scaled dual variable. Okay, so we're going to define W to be U over rho, and we're going to write things in terms of W. So that's called scaled form 8mm. It's really the form most people use. In scaled form, the augmented Lagrangian takes this form. You can say I have no term that's the inner product between U transpose, between U and AX plus BZ minus C. That's because if I look at just this piece alone, AX plus BZ minus C plus W norm squared minus rho over 2 W norm squared. If I have W equals U over rho, right, and if I expand this out, then I get rho times W transpose AX plus BZ minus C plus rho over 2 AX plus BZ minus C norm squared. And the term for the norm of W squared canceled with this one. So that was the cross term. That was the square term for this piece. And then the square term for W canceled here. And this, remember, this right here is exactly U. So this is what we had before. So it's just a rewriting of what we had before. But it's a slightly more convenient form. I've gotten rid of the cross product in my definition of the augmented Lagrangian. And now the updates just become minimize this over x, minimize this over z, and make a dual gradient ascent update. But where I had u equals u plus rho times the residual, now I have w equals w plus the residual. Right? Because if I divided both sides by rho, then u over rho became w, and this thing didn't have a rho in front anymore. And it's just often we have to think about fewer terms in this formulation. That's why it's more convenient. Okay, so the only terms that matter for the x minimization is f of x plus this piece. The only term that matters for the z minimization is g of z plus this piece. And then the gradient ascent update is this. Okay, and one thing that will be helpful when we talk about consensus ADMM next time is that in this formulation, the kth iterate in the dual here is just a running sum of residuals. Okay, it's whatever it was when we initialized it plus add up all the residuals I've seen so far. Right? That's just kind of repeating or unraveling this equality here. Okay, let me give you an example of how this can be applied, and it's a very simple example, and it's to find a point in the intersection of convex sets. Okay, we want to find a point that lies in the intersection of convex sets C and D, and we actually already saw how to do this. So we saw that we could actually rephrase this as the criterion being the maximum distance to each of the sets. And we could apply the subgradient method. And with a particular choice of step size, this was like way back when we talked about the subgradient method, we got alternating projections. So project onto C, project onto D, project onto C, project onto D, etc. It's a famous algorithm from due to von Neumann. So that was one method we know for finding a point in the intersection. It's just alternating projections. And now we can ask, well, what do we get with ADMM? Okay, what would ADMM give us? And we're going to write the problem in a slightly different form now because we want it to be decomposable. We want the criterion to decompose into something like f of x plus g of z, and we want to have an equality constraint. And so I'm going to start off with just the criterion being the indicators of x plus the indicator of d, another convex set. And now I'm going to introduce an auxiliary variable z. So this is a very common trick, which is why I gave this example. We're going to often have problems without equality constraints, and we're going to introduce them so we can apply ADMM in a particular way. Very similar to how we derive duals for unconstrained problems. And here I've plugged in for z here in the indicator for d, and I've introduced the equality constraint x minus z equals 0. Okay, so trivial rewriting of the problem. And now ADMM involves the following steps. Minimize the augmented Lagrangian over x. So what is the augmented Lagrangian? That's going to be, in this case, we have the indicator of c for f, and this just becomes x minus z plus w. Right? That's what this term looks like. The norm of x minus z plus w. Okay, that is actually projecting z minus w onto the set C. Right? If I minimize that over all x, then the indicator forces me to be in the set C. And if I minimize the squared loss subject to being in the set C, it's just the projection of z minus w onto the set C. So that was just reading off somehow this update for this problem. And similarly, the z update is to project x plus w onto the set D. Okay, and this is, note the most recent value of x. It's xk, the one we just solved for. And the dual update is w equals wk minus 1 plus x minus z. Okay, so it's like alternating projections. It's very much like this alternating projections method, except it has a dual variable. So it actually has an important distinction. And people who work on projection methods call this sometimes an offset variable as well. It kind of offsets what you're projecting. And in fact, this ADMM algorithm converges much quicker than standard alternating projections. So it's already a sign that somehow augmenting the Lagrangian and invoking duality is giving us something that converges a bit better. And one kind of specific way to see that is to think about the case in which one of those sets is a linear subspace. So if C is a linear subspace, if I have a linear subspace for one set and I have a generic closed convex set for the other, then it turns out that actually I do not need to write W in this first projection step. Okay, due to linearity, it kind of doesn't matter what W is here. Something that you can check. So I just gotten rid of that in this projection step here. And this is now actually exactly the same as what is known as Dijkstra's algorithm for projecting onto C intersection D. And Dijkstra's algorithm is an old method that came after von Neumann's algorithm, but was kind of specifically designed to have better convergence properties than alternating projections. So ADMM kind of recreates that just as a special case by chance for this projection problem. Okay, so this is going to converge in a lot more generality, let's say, and a lot faster than von Neumann's method. All right, so I have 5 minutes left. I think it's probably not worth jumping into the next lecture. Maybe I'll just talk a bit about scope. And I think this will make more sense next time because we'll talk about, I have specific examples of applying ADMM in various problems compared to coordinate descent and other methods like that. So let's maybe just talk about first order methods, second order methods, coordinate descent, and ADMM. Those are kind of big classes of methods that you might be using. I'll repeat, this is only going to take like 3 minutes. You guys can still leave early, don't worry. I'll repeat something that I mentioned earlier, which is that first order methods and second order methods, we can think about these as a kind of very heavy machinery we can apply to optimization problems. Okay, so interior point methods can be applied to essentially any problem you write down. After sufficient kind of reparameterization, you can apply an interior point method. So they're very generic. So that's what we like about them, is that, you know, if you think about a convex problem and you think, oh, this is a cool problem, I want to solve it, you can probably use an interior point method to solve it. There's probably, you know, it's probably going to work. It's probably going to be slower than a specialized algorithm, but it'll work. And that's the advantage of somehow these formulations like disciplined convex programming, like in CVX. So I would say that would be my consideration for second order methods and interior point methods. For specific problems where the Hessian has lots of structure, that's when I would start to think about interior point methods becoming competitive in practice. So if I had a problem which I knew that the Hessian was banded, or if it was sparse, or if it had some nice structure like it was circulant or something else, like I knew I could solve linear systems in it quickly, then I would stop thinking about interior point methods as like a prototyping algorithm, and I would start thinking about them as a projection algorithm. So that would be my consideration for those. Now, first order methods versus coordinate descent versus ADMM, that's a tricky comparison, but I would say that first order methods, like the generic ones we've learned, they also have the advantage of kind of being more general. So getting a method in a particular form which we can apply proximal gradient, that's generally something we can do more easily than apply coordinate descent. So coordinate descent, just to kind of remind you or give you the recap, we think about it applying to problems like quadratic plus separable. Okay, whereas proximal gradient applies to problems which are smooth plus, maybe we'll call it proximable, something that has a prox that we know. So it's a more general structure. And the choice of coordinate descent over proximal gradient, I would make that based on how quickly I can do the coordinate updates. If I can do the coordinate updates at a cost that's kind of roughly close to one proximal gradient iteration, it's probably worth it. It'll probably converge faster, even with acceleration, in my experience. So it's all about something like the implementation trick going from one coordinate update to the next. Now, ADMM is, it's a tricky one to answer because, as I'll motivate next time, it converges very differently depending on how you make this decomposition. So in this problem, there's just like one choice for the decomposition. In general, there's a lot of ambiguity. So just like deriving duals, you could plug in auxiliary variables in different places. They actually lead to different behaviors in terms of conversions. So I would say ADMM I would put roughly on par with first order methods, which means that they would converge slower than coordinate descent when coordinate descent is applicable. But the big advantage of ADMM is that I have the kind of flexibility of designing an algorithm and improving it. So I can try one kind of formulation for ADMM form, and if it doesn't work so fast, I can try a different formulation, and I might get quite a different convergence behavior, which I'll demonstrate next time. And the biggest kind of reason to know about ADMM is that for many problems, we can put things in a parallelizable form. So I haven't gotten yet, like you haven't seen anything yet that mimics this. Right, this is the point of dual decomposition. You haven't seen this yet for ADMM. You haven't seen how it can split up across kind of B processors. That is possible with something called consensus ADMM. And so that would be, maybe it's one of its most important features is that you can often set up things to be parallelizable. So if you're in a parallel computing structure, then it's a very good thing to use ADMM. Okay, so that was hopefully comprehensible to some or some fraction that was comprehensible, but I'm happy to discuss this offline too. And next time we will get to 8 mm in depth. So I will see you guys then.